Hey guys, this is going to be an introduction to resonance structures. First, I'm going to teach you how to draw resonance contributors, and then I'm going to let you guys know how to determine which contributor will contribute most to the hybrid itself. And we know the hybrid is what exists in nature. So, to draw resonance structures, you kind of follow 4 different rules. So, 4 rules. The first rule is that atoms never move. Only electrons move. The second rule is that only pi electrons and lone pairs can move. So only pi electrons, electrons in pi bonds, and lone pairs can move. The third rule is going to be the total number of electrons in the molecule doesn't ever change. So you keep the same formal charge when you start and when you finish. So the total net charge remains the same. The fourth rule is basically another way to say the second rule, and it's that sp3 carbons cannot accept electrons. That's basically the same thing as the second rule, only pi and lone pairs can move, but sometimes it's a little bit easier to understand if you just think about it that way. The sp3 carbons cannot accept electrons. Alright, now that we have 4 rules, we can go ahead and try to apply these to some problems. So the first one is I'm going to have to draw some resonance structures for this compound. CH3CH. Alright. Now the first step to do is we identify all our sp2 carbons, and this is sp2, this one's sp2, this one's sp2, this one's sp2, and this one's sp2. This one right here is sp3, so we can't do anything with that area. So what we can do here is we can move one of these pi electrons over right here. And if we do that, the whole part of the molecule stays the same, except this area. Now it's just a single bond, the pi bond moved to be over here. So now there's no positive charge on this carbon. The positive charge is now going to be on this carbon. So the second thing that can happen is these pi electrons over here can move like that, and you get another resonance contributor. So now there's a single bond between carbon 2 and 3. Now a double bond between carbons 3 and 4. So there's no more positive charge here. The positive charge is now on carbon 2, assuming we do 1, 2, 3, 4, 5, 6. This is CH, and then alright, so these are 3 resonance contributors. And now drawing the hybrid, any point where we had pi electrons that moved, we can draw them as dots. So like that's how you draw the hybrid. So it goes CH3, single bond, CH. So between these 2 areas there was a pi electron that moved, so you do a couple lone pairs, or not lone pairs, you do a couple electrons like that, dotted electrons, and they appear like that. Another one between these two. So you get what I'm saying. So each one has hydrogen until you get to the end, CH2. Then they all share these electrons realistically. This is the hybrid. Alright, so now we can try a different or another problem. We'll do example 2. Try this compound. CH3. Alright, so using the first rule, well, not just the first rule, I guess, using our third or second rule, we'll take these lone pairs, we'll start there, and we'll go ahead and bounce them there. And then once that happens, we need to move this double bond onto a carbon. So we're moving the electrons inside the ring. And now, since you've made a double bond here from the lone pair, there's a positive charge on that nitrogen. So these are your two resonance contributors to the hybrid. So now, to draw the hybrid, any place there was a double bond before or after gets little dotted electrons. So we'll do an N, CH3, CH3. We'll do some dotted electrons right there, and we'll do some dotted electrons right there. And we'll do a partial negative charge and a partial positive charge on these right there. So this is the hybrid. Cool. So those are just general rules to how to draw resonance structures. Now I can show you how to determine which one will contribute most to the hybrid itself, because not all of them contribute equally. So determining which resonance structure contributes most to the hybrid comes from the resonance contributor stability itself. So there's factors that decrease the stability for the resonance structure, and there's 4 factors. Sorry that this camera's been wobbling, it's set up weird. The first factor is going to be having an atom with an incomplete octet. And a second rule is going to be a negative charge that is not on the most electronegative atom. Having negative charge that is not on most electronegative atom. The third is going to be a positive charge on an electronegative atom. And the fourth is going to be having separated charges. So anytime you see one of your resonance contributors having any of these characteristics, that means that that resonance contributor is not as likely to contribute to the hybrid as, say, another one. So we'll go ahead and do some examples so you guys can get what I'm talking about. So the rules here will be draw resonance contributors for each of the following compounds, and then we'll circle the one that contributes most to the hybrid. So we'll start with this compound. I'm just making them up. Let's see. All right. So what can we do? We can move a lone pair, or actually, no, let's see. We need to scratch that, take that. Move this pi bond electron onto the electronegative atom, and then we can move this double bond over here. So moving 2 electrons at a time. So you get a single bond, but now you have 3 lone pairs around this oxygen, so it has a negative charge. Then you have a double bond here now, but now you have a positive charge on this carbon. So between 2 of these resonance structures, we know that structure A or B, that A is going to contribute more to the hybrid because it has neutral, it doesn't have any separated charges, and this carbon right here has an incomplete octet. So those are 2 rules that violated in this structure, so this means that structure A is going to be more likely to contribute to the resonance hybrid. We'll try one more example, and then I'll have to cut the video. So for this one, let's see what we can do. Let's try to move this pi bond onto this oxygen to neutralize this positive charge right here. So, and then at that point, we can move this lone pair to make a double bond between the nitrogen and carbon. So our resonance contributor would be H with 2 lone pairs. There's no negative charge there, and now there's a double bond between carbon and nitrogen. No lone pair on the nitrogen. There's a positive charge there on the nitrogen. I don't think we can make any more resonance structures for this one. So which one will be more likely to contribute to the hybrid? We can look at rule 2. The positive charge here in structure A and in B, in A, it's going to be on the oxygen, and on B, it's going to be on the nitrogen. Nitrogen is a less electronegative atom than oxygen, therefore it's better at accommodating a positive charge. So that means that B is going to contribute more to your hybrid. Thanks for sticking around, guys. I know this